Today we'll be looking at properties of vectors. To begin, let's look at a couple properties. First, we'll look at the cumulative property of addition, which states that we can add vectors in any order. So let's look at a plus b and b plus a. So if we have our shape here, and we can label it a, b, c, d. Here we have our vector a, and our horizontal will be our vector b. And this here, okay, would be our diagonals, alright, which would be a plus b. So let's look at our AC. So AC would be equal to AD plus DC, which is equal to B plus A. And if we were then to also look at AC, if we went in the opposite direction, so we went AB plus BC to get to C from A, we would have A plus B. So you see, B plus A and A plus B will give us AC. So therefore we can state that A plus B is equal to our B plus A. Now if we look at the associative property of addition, which states that when we change the groupings of vectors, the sum does not. So it states when we change the groupings of vectors, the sum does not change. So let's look at a plus b plus c and a plus b plus c. So just to give us a visual, okay, of such, if we have O, A, B, C, for instance, and say we're talking about our a plus c, and we have our vectors a, b, and c. So let's first look at a plus b plus c. So this is equal to OA plus AB plus BC. So by our bed mass, we know we need to deal with our brackets first. So that's OB plus BC, which will be equal to OC. And then we can look at our A plus B plus C. So this would be equal, our A is, OA plus our B, which is AB, plus our BC. Following bed mass, we're going to add the brackets first, so we get AC. So this is equal to OC. So therefore, since they are equal to the same thing, we have A plus B plus C is equal to our A plus B plus C. So now we can look at our first example. So we want to determine RQ plus SR plus TS plus PT as a single vector, given the following diagram, and using the properties of vectors with this diagram. So I'm trying to find here my RQ plus SR plus TS plus PT. So because order doesn't matter, I can change the first RQ and SR to SR plus RQ. And that comes from our cumulative property of addition that we looked up above. And similarly, inside the brackets I can do the same thing. So I can say PT plus TS. So now when I add these, I have SQ plus PS. Again, use the same property of the cumulative property of addition, and therefore I can state PS plus SQ. So this is equal to PQ. So that's my single vector. So now we can look at the distributive property of addition, which states that when we multiply the sum of vectors by a scalar, it is equivalent to multiplying each vector by the scalar and then taking the sum. So recall from yesterday when we had our scalar k and we multiplied it by a plus b, this was equal to k times a plus k plus b. Or sorry, plus k times b. So in our example 2 here, we want to simplify the following expression. So we're going to use our distributive property there, distribute that 3 into each term inside of our bracket, and then it's likely the same thing as we do in the first case. We're going to take that negative and apply it to each term inside the brackets. So here we are going to go ahead and simplify. So 3 times 2a is 6a plus 3b plus 3c. And then we're going to apply that negative to each term. So negative a minus 3b plus 2c. Now we can collect all our like terms here. So we get 5a. The b's are going to cancel out. And then we're going to have plus 5c. I can factor out a 5 here and I'm left with a plus c. Also just note on our side here, okay, where I'm starting, just it shows our properties of vector addition that we have discussed already. And also in doing the calculation in example 2, assumptions were made that we can implicit by that should be stated. So for example, if m were to be equal to 2 and n were to be equal to 3, we could just sub those values in there. So further laws of vector addition and scalar multiplication. So if you're looking at your associative law for scalars, mn times our vector a is simply just mn. You can have that multiplied together first and then multiply it by your a, or you can multiply your scalar n by a and then multiply it by the n. And then the distributive law of scalars, which we just discussed, we just take your scalars m and n and both multiply them by a. And also looking at your properties of the zero vector. So if you're adding the zero vector to another vector such as a, it will just be equal to a, and each vector a has a negative a vector such that a plus negative a would be equal to 0, hence your zero vector. Now a couple more examples here. Example 3, if vector x is equal to 3 times vector I minus 4j plus k, and y is equal to j minus 5k, and z is equal to negative I minus j plus 4k, we want to determine each of the following in terms of I, j, and k. So if we have our vector x plus our vector y, we're just going to sub in for what those vectors are actually equal to, and then we're just going to collect any of our like terms. So x is equal to 3i minus 4j plus k, and y is equal to j minus 5k. So then we can collect our like terms here. We only have one I, so you have 3i minus 3j minus 4k. And the next one that we can look at, sub in for your vectors x, y, and z. So x is equal to 3i minus 4j plus k minus 2 times our vector y, which is j minus 5k, plus 3, and sub in for your z vector. And then we can simply expand and then collect like terms. So multiply that negative 2, so you have negative 2 times j plus 10k, and then multiply that 3 in, so you have negative 3i minus 3j plus 12k. And then when we collect our like terms here, we're going to have negative 9, sorry, that should be a 9, not looking like a J, negative 9J plus 23K. And for our last example, if x is equal to 2/3 y plus 1/3 z, and x minus y equals a, and y minus z is equal to b, we want to show that a is equal to negative 1/3 of b. So what we want to do is we're going to take our first equation and sub it in to our second equation for x. So we're going to do exactly that. So we have 2/3 y plus 1/3 z minus y is equal to our a. So we have 2/3 y, and we can minus 3/3 y plus 1/3 z is equal to our a. So now we can collect. So we have negative 1/3 y plus 1/3 z is equal to a. And then we can factor out that negative 1/3, and we're left with y minus z is equal to a. And therefore, we would have negative 1/3 b is equal to a. So you notice here, you can sub in at that last step because we know that b is equal to y minus z. And that is the end of our lesson for today.